Welcome to the second installment of the Travel Time Reliability video series. In this module, we'll learn about the importance of observing conditions in the study area of your project. This analysis is critical as it ensures you are including the right geographic area, timescale, and variety of conditions that influence travel time reliability. The major steps in the process are recognizing the influence of upstream and downstream bottlenecks and understanding the importance of including a variety of operational conditions. Before we can assess the spatial and temporal scale needed for analysis, it's worthwhile to take a step back and examine the problem statement. The objectives of the study will set the parameters for the analysis limits. For example, a suburban freeway that experiences moderate morning and afternoon rush hour congestion has recently received a lot of complaints for excessive travel delays. As the traffic engineer responsible for investigating these issues, you suspect it has to do with snowstorms last winter and some crashes and incidents. But how do you begin to isolate and quantify these different factors? The solution to capturing these influences and impacts begins by breaking the problem down into a few different questions. Is this a spot location study or a corridor study? How long does the analysis have to endure to capture all the events for the study? What non-recurring factors, such as weather, crashes, incidents, or roadwork, affect the travel times or major fluctuations in demand volumes? The process of identifying the spatial and temporal parameters for the study begins with observing the system, looking at the historical record of traffic incidents, congestion, and non-recurring events. From the initial monitoring, we'll draw preliminary conclusions about what sub-area of the network to study, what kind of data to collect, and the time frame that data will represent. Together, these spatial and temporal extents, along with other influence factors, make up the reliability space for your analysis. In addition, these limits will influence the granularity of your reliability analysis. Smaller study areas typically utilize shorter time intervals and higher resolution traffic data, while larger analyses are often completed with less granular information. Now that we have a basic understanding of the reliability performance, it is time to think about where further evaluation should be performed. This will allow you to look at these issues in greater detail and begin the process of evaluating solutions. There are many tools available to visualize daily traffic conditions, such as heat maps, cumulative distribution curves, or travel time histograms. Speed band charts show the mean value speed as well as the variance between the 5th and 95th percentiles. This variance can be roughly thought of as the reliability of the facility. Begin the process by identifying reasonable limits upstream and downstream of the primary point of concern, where conditions are beyond the core reliability issues. These limits are characterized by locations that no longer experience the unreliable travel times caused by the influence factors in the focus area. Then, approach the temporal question by capturing critical times of day that include the formation, duration, and dissipation of highly variable travel times. Select a time period for the data collection that will include historical data from one or more periods known to include causal factors that led to interest in performing the analysis. This should typically include a particular season of the year, an entire year, or perhaps even multiple years. A longer time period should always be considered to ensure that any potential deficiencies are captured in the review. Now, incorporate the influence factors suspected to impact travel time reliability in the geographic area and time frame of your observations. You likely have some ideas of what these factors are, but similar to the time frame question, be sure to cast a wider net to make sure any additional factors are also captured. At a minimum, the influence factors you will want to include consist of weather records to capture precipitation events like snow and heavy rain, as well as other environmental factors like fog, sleet, or ice. The National Weather Service is an excellent resource for historical weather data. Continuous weather records for specific monitoring sites can be downloaded from their website, accessed from the link shown here. The records are often available in 5-minute increments and a variety of other time scales. Next, introduce crash and incident records to identify when capacity may have been compromised by these factors. Depending on your jurisdiction, these records may include detailed data about whether lanes were blocked or the type of emergency response that was deployed to resolve the situation. At a minimum, the date and approximate time of these events must be known to determine if travel times were affected. Roadwork history should be reviewed in the study area. Types of roadwork can range from short-term maintenance and repairs to major highway construction. Records can be obtained from the operating agency and should provide enough detail to assess when conditions were affected. Finally, fluctuations in traffic demand should be included. This can be approached in 2 ways, and using both is ideal. The first is to use vehicle detection within and around the study area. This could include inductive loop or microwave detectors and possibly GPS probe data, which is emerging as a reasonable source for a sample of traffic volumes. GPS probe data is available to state DOTs and MPOs through the National Performance Management Research Dataset, covering the National Highway System. There are also a number of commercial vendors that can provide comparable data on lower functional class roadways. The second is to identify major events that may have caused surge in traffic volumes. Sporting event schedules or records of other events at large venues like stadiums can provide this information. Let's look at a real-world example. Planners in Washington, D.C. wanted to expand the use of a static part-time shoulder use strategy from just the AM peak hours into a dynamic strategy that can be utilized at any time of day. By examining the afternoon peak hour speed heat map of the entire study corridor, several segments with heavier congestion were identified. The focus is the afternoon and evening peak hours of 4 p.m. to 7 p.m., as there was no change to the implementation of the shoulder use strategy during the morning peak. Downstream of the hard shoulder use at approximately milepost 28, and within the hard shoulder use area around milepost 18, are 2 key links and will be used for detailed analysis for our purposes. Similar to the spatial scoping above, temporal scoping was conducted to identify critical time periods. First, the daily speed heat map for a single segment is shown in here. It is evident that from September 2014 through September 2015, there is heavy congestion during both the morning, midday, and afternoon hours. However, with the implementation of the dynamic shoulder use strategy in September 2015, the midday and afternoon congestion almost completely disappears. Side-by-side comparisons after September 2015 show that the travel times in the midday and afternoon hours have drastically decreased. Reliability-centric data and visualizations are quite helpful for confidently setting the spatial and temporal limits of your analysis. Without these data and visualizations, there would be a lot more guesswork involved, increasing the risk of your project producing misleading results. In Module 3, we'll look at selecting the appropriate analysis tool according to the resolution of the data and the type of question you want to answer.